For this big picture in chemistry, I want to look at the mole and tie together some ideas behind mole conversions into moles, getting out of moles, that get introduced throughout a chemistry course, so we can look at some examples and try and figure out which is the most appropriate conversion to use, and which ways may be more common sometimes and which ways may be less common sometimes. And so to start with, I want to introduce this visual of a maze to the mole. Of course, there's lots of different ways to express amounts, but balanced chemical equations are expressed in terms of moles or mole amounts or mole ratios. And so I'm going to look at four main ways that amounts get expressed and how we can convert each of those to moles, and then talk about how to use this mole maze to make a map from where we start in a problem and where we end up in a problem, and then we'll apply it to an actual chemistry problem. So the first way that amounts might get expressed is as atoms, right? We could have individual atoms or individual molecules. Now, in a real-world scenario, we're not usually worried about individual atoms or molecules. We don't usually have individual atoms or molecules. But in chemistry problems, sometimes they're phrased in terms of how many atoms is this, how many molecules is this, or this is this many atoms. Okay? Another possibility is we're in a lab and we have some solid, and its amount is expressed in grams, or we put it on the balance and we get a gram unit out of it. Okay? Another possibility is that we have a solution, a combination of an aqueous solution or something like that, where we might know, so we might have a solution, and we might know the volume of solution that we're reacting. And a third situation that we might have is maybe we have a tank of a gas, right? We know the pressure of the tank, we know the volume of the tank, we know the temperature of the tank. Okay? And so this is for gases. Okay? And so each of these different starting points has a different path to get from that amount to the mole. If we're starting with individual atoms, the pathway, the conversion factor that gets us to the mole is Avogadro's number. It's that 6.02 times 10 to the 23rd. And the units on that are atoms or molecules or pieces per mole. So this up here, I wrote atoms, but it can be anything per mole. So we can multiply by that or divide by that to get to moles or to get back to atoms. And so this is a bidirectional pathway using Avogadro's number as a conversion factor. If we start with solids, the conversion factor from grams to moles is the molar mass. The molar mass is different for each substance. We just have to add up the average atomic masses for the formula, and we get the molar mass. The units on molar mass are grams per mole, and so we can divide by that or multiply that by that to get either into moles or back into grams. For solution, if we know the volume of a solution, the conversion factor that gets us to moles is the concentration. Concentration is usually expressed in molarity with a capital M, which is moles per liter, although there are other ways to express that. If we take concentration times volume, we should get moles. Okay? And then lastly, if we know the pressure and volume and temperature of a gas, the conversion into moles is the ideal gas law. Pressure times temperature equals moles times the gas constant times temperature. So pressure times volume equals moles times R times temperature. Okay? And that will get us either 2 moles or back to maybe a volume, or maybe they want to know the temperature or something like that. So now we have all these different pathways to get from moles and to get back out of moles. I should emphasize that these are all bidirectional. We can use this maze to figure out where we are starting in a problem, how we need to get to moles, and how we're going to get out of moles, because most of the time a problem doesn't ask for how many moles of product. It asks for what is the volume of product, what is the mass of product. Okay? Of these 4 ways, the least common is atoms and molecules, and the least important of all these conversion factors is Avogadro's number. So if you're stuck on a problem, don't start multiplying by Avogadro's number. Maybe pick the molar mass instead, or some other conversion factor. So let's look at an actual problem and see how we can solve this using this molar maze map, right? So the problem says sodium bicarbonate, when it's heated, releases carbon dioxide gas. What is the volume of carbon dioxide produced by heating 5 grams of sodium bicarbonate at 180 degrees Celsius and 1.3 atmospheres? Now the first thing I'd like to do is just copy down the information about each substance. So for sodium bicarbonate, we know we're starting with 5.0 grams of it. For the carbon dioxide, we know a final temperature of 180 degrees Celsius, and we know a final pressure of 1.3 atmospheres. What we're trying to find is the volume of that. So let's go back up to this mole maze, and let's identify what our path is going to be. We start with a solid, so we're going to need to use the molar mass of that solid to get to moles of that substance. Once we have moles of one substance, we'll use the balanced equation to convert to moles of any other substance. Okay? And then from moles of that substance, we need to find the volume of a gas. So we're going to use the ideal gas law to go this direction to find that volume. Okay? So let's go ahead and do that now that we have our pathway planned out. The first thing we need to use is the molar mass for sodium bicarbonate. You can add 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens, has a molar mass of 84.01 grams per mole. And so we can set up a conversion from grams to moles like this. 5.0 grams times, or divided by really, 84.01 grams per 1 mole. And this tells us that we have 0.0595 moles of sodium bicarbonate. Okay, now that we're in moles, we can take care of any conversions to other substances. Right? So we know how many moles of sodium bicarbonate we have. We want to know how many moles of carbon dioxide we have. Well, in this equation, the coefficients are 1 for each of these. So we have 1 mole of CO2 produced for every 1 mole of sodium bicarbonate. And that means we must have the same number of moles of CO2. The last thing we need to do is convert moles of CO2 to volume of CO2. Remember, if we look back at our mole maze, to do that we'll use the ideal gas law. And I'm not going to fully cover the ideal gas law here. I will say that first we need kelvins for temperature, so we'll need to convert this to kelvins by adding 273. Okay, and our gas constant R is equal to 0.08206. So the way this equation sets up is that the volume is equal to our moles, 0.0595 moles CO2 times R, which the value is there, times our temperature, 453 K, and divided by our pressure, 1.3 atmospheres. When we solve that, we get a volume of 1.7 liters of CO2. So we used our mole maze to map out a plan to get from amount of a solid to amount of a gas in the same reaction. Okay? Hopefully that visual will help you think, I need to get to moles. How can I get there? What's the appropriate conversion factor to use? And hopefully that'll help you dissect these sort of more advanced problems that use multiple different phases of substances, solutions, gases, solids. Right. Hope that was